Our next speaker, Stephen Irish, has substantial experience in battery technology development and product delivery, having worked in Tier 1 automotive supply chain companies, OEMs and engineering consultancies. He is the founder of Sunderland-based Hyperdrive Innovation, whose battery management technology is used in a host of different applications. He will now speak about the evolution of battery technology.
As just explained, I'm Stephen Irish. I'm the founder of Hyperdrive Innovation. I'm going to talk a little bit about batteries and the things that we put them into at Hyperdrive. I'm going to tell you a little bit about the who and, importantly, the why of Hyperdrive, and just skip through a little bit of history of battery technology, touching on a great conspiracy that probably never happened, which may be of interest, a bit about the current state of the art in batteries. And having done some history, I promise to take you back to the future as well. And also to hopefully answer the question which no one's asking, which is faster, diesel or EVs? So maybe something a little bit amusing at the end of the presentation. So the reason we started Hyperdrive is that we could see the way in which energy was being used, consumed, distributed was changing completely. We started 6 years ago. And we'd been talking about EVs for a long time before that. So I had my final year thesis over 20 years ago on EVs. It was probably a little bit early, and I had to go and get a proper job. But since then, the world's moved on. And there was a time when we used to have to argue about if EVs were coming, electric vehicles were coming. Now it's really just a discussion about when. And as the previous presenter, as Chris mentioned earlier, that there's a true disruption in terms of the autonomous, connected and electric vehicles. That's the way we see things going, but also how they're connected, how they are charged, and how energy is generated, stored, consumed, distributed is completely changing. So that's really led us to where we are, which is we're a technology supplier of lithium-ion battery technology, but we work with customers to help them integrate it into their systems. So we're a complete solution provider. That means that we're kind of two key areas that we divide our activities into, and they're the things that move and things that don't move. So for us, the things that move, the vehicles is quite a broad church. So we're involved in electrification of factory robots. It could be passenger vehicles, it could be all sorts of other things that I'll touch on later in the presentation, but also the things that don't move, so stationary energy storage. So it's a theme which is really growing now, how you might store energy in your home if you generate solar energy, or on a larger scale in a business or a network or infrastructure level. And you can see as the increase of renewable energy, energy storage becomes an enabler for more renewable energy to be used. So, a little bit of history. Electric cars have been around for a long time. This picture's from 1913. That's actually Edison stood in front of it there. And EVs predate that. Lead-acid batteries, of course, at that time. So, a technology which is still around today. They were prevalent for a long time and still used a great deal. They'll start the engine in your car at the moment, a lead-acid battery, but they're also used in industrial machines, forklifts, things like that tend to be prevalent. But they lost their dominance, EVs, due to limitations on range and also speed performance. This would have gone less than 20 miles an hour, very limited range. So for most of the 20th century, the dominant EVs have been milk floats and forklifts. So moving forward a little bit, skipping through history, fast forward to 1996. This is truly a groundbreaking car by General Motors, the EV1 in 96. It's difficult to believe, really. It really was truly groundbreaking, very exciting car at the time. It was electric, it was aluminium, very light, very low drag, slippery shape, unusual styling to achieve that. Initially, again, with a lead-acid battery, if you think in that gap between the first picture and the second one, but latterly with nickel metal hydride technology. So it was really brought about by General Motors because of, at the time, what was known as CARB, the California Resources Board, which was legislation that actually never came to pass. But at the time, it put all the big car makers under huge pressure to come up with ideas about how they were going to reduce emissions. This is 1996, remember, and never came to pass. So that leads into the great conspiracy, because all these cars that were built and leased and had some very passionate advocates were withdrawn by GM and crushed. They were destroyed by GM. And that leads people into the great conspiracy theories about why that happened, and what was it the oil companies that led that to happen? Was it a conspiracy between the big three car makers in the US, or was it simply because the battery technology wasn't quite as good as it needed to be to roll out into mass production and to sell? There's an exciting, really interesting documentary called Who Killed the Electric Car, if anyone's interested to hear more about that. It's interesting. And the sequel, which was The Return of the Electric Car, of course. And we can't talk about EVs without the T words. It was in the previous presentation. So this is Elon Musk's very own Tesla Roadster being blasted into space on SpaceX's Falcon Heavy. Who knows where all that'll end. It's true to say Tesla really has been a disruptive influence on an industry that doesn't really like change. The automotive industry's quite risk averse. They only change when they really have to, and Tesla has given everyone a real run for their money. Tesla, like most EV makers these days, use lithium-ion technology. So I just put this chart up to kind of explain a little bit about what these different technologies mean and the evolution of them. So bottom left there, you can see lead acid, and the top right is lithium-ion, where most people are now. And critically, there's three factors, but two shown on this chart. You want them to be lighter, and you want them to be smaller, because the more you can squeeze in, the more further you can drive, but also the better the performance of the vehicle. So you can see huge jumps forward between those early lead acid technologies through to lithium-ion, where we are now. This takes you through to the Nissan Leaf battery. So this is manufactured in Sunderland, where Hyperdrive are co-located, mass manufactured by Nissan. And of course, the third key category that wasn't shown on that chart is the cost. So this battery pack this is the original Nissan Leaf. It's had several incarnations, and the most recent one that was recently launched at the battery, which is manufactured in the UK, something we should be extremely proud of as a nation. Hyperdrive are a customer of Nissan, so we actually buy the battery cell that goes into the Leaf, and we incorporate it into our own products. They've made some huge jumps forwards in the amount of energy, also the cost per kilowatt hour, that critical metric. How much does that energy cost you? So there's nearly twice as much energy, and for about the same price as there was when they first launched the Leaf, which, as you can see, is a big jump forwards. So we use that technology. We hang on the coattails of that huge investment made by Nissan in the UK to manufacture our own product, which is a battery system which is modular, incorporates their cell, but critically uses our own design of the pack and the battery management system, the electronics, the brain that sits within that battery and looks after it and gives it the best possible performance and the longest life. And the sorts of applications that we take it into include off-highway, so construction equipment. It could be municipal equipment and factory robots. Everything is being electrified. Here's one example of a project we did last year. So you can imagine something which is currently got diesel technology, quite old-fashioned diesel technology we can electrify. It means it can operate quietly, you can operate inside, you can run them earlier in the morning, later at night, and you're not going to bother people. So a number of themes that we see in kind of non-passenger vehicle. So it's pretty much anything that's working in cities. And also at airports. So this is a project we did with Douglas Equipment, another British company owned by Textron in the States. This is what they launched last year. So originally this was a 1,000 horsepower diesel pushback tractor. So as the aircraft move onto the runway, before they started up their main engines, they'll typically get towed out by a vehicle like this. And airports are very keen to reduce the emissions. It counts towards the overall reduction of CO2 and particulates for air travel. So we hybridised this one. It meant you could have a much smaller engine. A lot of the time it can operate in pure electric mode, and you're not so reliant on diesel fuel. So gives you running cost advantages. There are fewer parts to service, but also critically, you're not moving fuel on and off the airport area, which means there are also security advantages as well. So both those products I've just showed you, they critically use our standard modular battery. So they're able to deploy it into lots of different markets without having to re-engineer it every time. Slightly busy slide here, but this is just to show you what the outlook is for the future. This is produced by the UK Automotive Council and the Advanced Propulsion Centre, who are part of the sort of arm's length organisations from government to help deliver some of this new technology into UK companies. And they've set out the kind of roadmap of where they see this technology going. I won't go into detail, but it'll be available in the slide pack, a really useful reference document, some really useful data that the APC and the Automotive Council produce, giving some indications about where that cost per kilowatt hour and also the energy density are going to get to and how one might get there. What's exciting is there's no one solution. So if you're a smaller company and you're disruptive and you want to make an impact, there therefore is opportunity. And the red area at the bottom is where Hyperdrive are focused on. It's mainly at a pack level, but we're also very interested in what happens when the battery comes out of what's called its first life. So although the manufacturers may be saying the battery will last 10 years, it still has life in it at that point. So you may have reduced range, but you could take that battery out and use it somewhere else, perhaps in stationary energy storage, perhaps to store solar energy. So it's the second life we're interested in as well. And also what happens at the end of life. How do you take those materials out and recycle them and make use of them? So if we can create a second life value, a second-hand value, the residuals of the vehicle improve, and also there could be a whole business around that. So we've invested a lot of technology in how to deal with the cells when they're new, but also when they get to the end of their first life. This just brings me on to the last bit of fun, really. A number of years ago, Johnny Smith on the right, there's a journalist who approached us and asked if we would help electrify a car with him, and behind us there is the flux capacitor. So he wanted to build the fastest street legal electric car in the world, which we did with him, and he pitched up with that, and we said, oh, really, you probably wouldn't start with a car like this. So this is the Enfield 8000, which was one of the first EVs produced in the UK on the Isle of Wight in the 70s. And was run via various electricity boards, and then disappeared at the end of the oil crisis, I think. So that was his start point, and we helped him build an extremely quick. At one point, was faster than the fastest mode that you could get on your Tesla, on your P85D. So it was quicker than, I can't remember what the mode was at the time. And then of course they had to bring out an even faster version. It's not a particularly practical car, as you can see, the size of Johnny. It was kind of folded up inside this car when he took it down Santa Pod. But there's a short video clip here just to show you a little bit about which is faster, whether it is EV or diesel, which of course is the question everyone wants to be answered.
So why not have a good old-fashioned showdown? It's fossil fuels versus the future. Well, kind of. Oh yeah, and I forgot to mention that it's also road legal. Although I do have to remove the wheelie bars, otherwise it's not classed as properly street legal. So if the police are watching this, I will remove those, I promise.
Mark James here from Liberum. In terms of the relationship with Nissan, how obviously beholden are you to them? So if they move to a different technology, change the format, you've got all these modular products, how would that affect?
First of all, we have a number of different cell suppliers, so we always left ourselves that option. In fact, the ones in the flux capacitor, because of the performance of it, we had to use a different cell. We have a supply contract with Nissan. We're the first company externally, which is something we're very proud of. Took a while to negotiate, you can imagine. They've been excellent in terms of sharing their technology roadmap with us, so we actually have visibility of what they're going to be doing or potentially going to be doing over the next few years with cell formats, cell types, and they're actually taking information from us and our customers as well about where they might go in future. Nissan are divesting their battery business. It's going to become ASEC, so it's been in the news already. So there's 3 sites globally that produce the technology, and we can draw down those cells from any of those 3 global locations. So we think it's well mitigated. We are part of their capacity planning. It's a big fundamental strategy change for them to have other customers other than Nissan, and that's part of their business plan. They want to significantly grow the volume, they want to get the economies of scale, and they recognise the amount of investment that's required to achieve that.
Thank you. Can I just follow on? We didn't really touch on it, but in terms of in-home storage, would you work with them in terms of, again, using their cells in terms of end of life of a car, but putting it into the home? Do you do
yes,
that?
yeah, we can and we are. So yeah, the technology that's in that device was developed by our team.
Hi, yeah. Just a question about Nissan, really. Range anxiety is always a big problem for the petrol consumer at the moment, or diesel. What does the next sort of 3 years look like on a standard battery-powered car? Because at the moment it's like 200, 250 miles maximum. Is the battery going to become cheaper and much longer range and lighter? What does a picture look like, say,
Sure.
2 or 3 years down the line?
I mean, that trend's likely to continue. So you think from the original Leaf to the current one, there's nearly twice as much energy in it, nearly twice the range. There's always caveats. It always depends how you drive. I drive an EV every day. They're quick, they're fun to drive. That leads you into a particular driving style sometimes if you're into your cars. I think driven conservatively, you can get the advertised range out of them. I think range anxiety is very interesting because of often it's more of a perception than the reality. But because I'm an engineer and I always test the limit cases, I have run out, and it is a pain. It's not the same as going to fill your car up with diesel or petrol again. But the studies that we're involved in right at the start, most people perceive that they're driving further than they actually are when you poll them, and then as you measure how far they drive. Batteries can get bigger. I mean, that's Tesla's solution, is an absolutely massive battery. It's heavy. That's not necessarily the best solution all the time. You can just get bigger and bigger batteries. They are getting more efficient, they're getting smaller. But really what you want is the right size of battery for the job you're trying to do. If you're commuting daily in a city or something, it's highly unlikely you'd need hundreds of miles. Maybe you need something different at the weekend or for the longer journeys. So it's really about getting a battery of the right size. If you size it for the once a year journey or the twice a year journey, and then every day you're carrying that battery around with you, you're actually carrying that extra weight and cost around too. So I think people's driving habits, but their expectations of how vehicles will work will change, and touched on autonomy before. The ownership models are changing as well in cities with younger people not necessarily aspiring to owning their own vehicle. So you may even have different vehicles for different jobs, so shorter and longer range. But they're definitely getting better. It's definitely usable range now.
Aren't there limitations, though, on what lithium-ion can actually achieve?
It will tail off, and that chart I showed earlier actually has some different chemistries on as well beyond lithium-ion. None of them are kind of commercially viable at the moment, but huge investment going into the chemistry at the moment to improve it.
Perhaps a related question, solid-state batteries. I'm not sure that I saw that on the slide. Aren't there weight advantages and security, etc.?
Lots of talk about them, yes, and as and when they come to maturity. I mean, our remit is we're chemistry agnostic, we're cell agnostic, so we'll use the best ones that we can get our hands on. We've dabbled in stuff which is lab based, but until it can deliver the performance that our customers need, it'll stay in the lab. Our job's to make sure our technology can adapt and use the latest technology. So as and when solid state becomes available, but lots of these things are talked about, and trying to get your hands on stuff that works is sometimes a bit of a challenge. So I'm sure it'll come one day.
I would just ask about Second Life. How's that impacted by charging behaviour, and particularly if a lot of people are talking about vehicle to grid, putting the power back into the system? Won't that damage the life of the battery so that there isn't really an effective second life?
I think, first of all, the performance of cells when they're new and life is very good. It is affected by things like how hard you charge it, and also things like temperature. So they do affect life. And there were some early outlying cases in very hot states in the US, for example, where batteries didn't last as long as expected. There are solvable problems. A key thing with some of the technology we're working on is knowing a bit about being able to characterise those cells when they come out of their first life. It's unusual that they'll be unusable. It's likely there'll be a range of performance, and it's important to then grade them and then match them up as far as possible. What you don't want is really good cells with slightly iffy cells, because a battery pack's performance is governed by the weakest cell in it. So a lot of work we're doing at the moment about characterising second life cells, and some will be fine for sort of premium energy storage, and some might be downgraded and maybe used in other applications. So it's early days, because if you think the sort of mass EV sales has only really got going, it's a problem that's likely to manifest itself in years to come. But in terms of positioning ourselves as a technology company, we really want to own some of that IP, so we think it's a really exciting space. So we have quite a lot on our site at the moment of second life cells.
Perhaps I can ask a question. What's the next steps after a battery has finished its useful life?
Well, I think the key thing is to extend as far as possible, like the first and second lives, or the total life, and then you can share the cost and the energy that you've used to make that battery over a longer life, and then it's into more innovative ways of recycling and recovering those materials, so getting them back out from the battery cell, and that is a relatively immature area. So again, we're working with partners of how you deal with that battery when it comes to the end of its life. So the battery pack maker has the liability for that cell through its life. So it's something that's...
And do you have figures on first and second life of a battery as to how many years it might last?
Well, I mean, a typical, like their leaf cell there, will last thousands of cycles, but it is dependent on how hard you charge it. So people are interested in fast charging, but most people don't fast charge their car every day. You typically would charge it overnight, or in a car parking space during the day. So it is dependent on a number of factors. And just to give you a feel, if you discharged your battery, there we are. Need a backup battery. We were talking about power cuts earlier. It is dependent on how hard you charge and discharge your battery. So if you deep cycled it every time, you would last sort of about a third of the time, about a third of those 6,000 cycles. But if you give it a slightly easier time, which most people do, many thousands of cycles are easily achievable.
Just back on the range question. Do these modern technologies get over the problem of the fact that a battery driving a car in, say, northern Norway will not work nearly as well as something driving a car in the south of France? In other words, it's sort of heat dependent. Maybe the range is a lot less on a cold battery than it is in a cold environment than it is in a warm environment.
It's a good question, and it's true. So I mean, where I live, you readily see minus 15. It works, but it's a diminished range. We've got customers actually using, for example, snow moving equipment in Scandinavia. Typically, it's so cold there at night that that machinery will either be indoors or it may even be on a heater overnight. So the work we've done in Scandinavia typically be warming an engine up at, if it's like minus 40 or something, diesel engine isn't going to turn over. So you may be warming an engine or a battery or an interior of a vehicle off the mains before you start. And that's a good way of giving it that head start. The batteries will also warm themselves up. I mean, what you don't do is charge them or discharge them hard at very low temperature because it's damaging. But again, the BMS technology will prevent you from doing that. It recognises it's in that cold state and allows it to warm up gradually. But it can be solved by preheating And in fact, that's what my car does. It warms itself up the mains before I go in the morning. So I'm now not used to going out to a car with a frozen windscreen. When I get in the car in the morning, windscreen's clear, the interior's warm because it's warmed itself off the mains electricity. And then you don't need as much load on the battery, and also the interior's warmer.
If EVs become very popular, will there be enough lithium to go around?
And that's a good question, and you're seeing some of the battery suppliers now doing the full vertical integration, and they're acquiring the materials companies, even the mines that get the lithium. I think there needs to be more and more inventive ways of using these materials, and also the recovery at the end. I think it's immature at the moment. The means by which you deal with it at the end of life, there's more that can be done to recover that material at the end. But it's definitely a challenge for the industry.
Just a quick question, sort of a twofold thing really. The first thing is the standard physics behind the production of electricity in a lithium-ion battery is pretty well defined, and there's certain ways you can manipulate that to increase the range. How much more do you think you can push that with the development of the software, which is very key to moving this forwards? Is the one side, and I guess the second side is just for everybody in here. How many of you actually drive an EV?
I think in terms of, for example, squeezing more energy in, although the physics and the chemistry might be fixed, there are efficiency gains to be had, and some of the early implementations were quite conservative, and so you can squeeze more energy in. So, for example, the Leaf Packard there from the early generation, the 24 kilowatt to the 40 now, it's the same physical size of battery. Essentially, it's the same chemistry. There's some tweaks to it, but the physical density of how many cells can be packed into that space has improved hugely. And you're right, the efficiency of, for example, your motor, the inverter, like engines, their efficiency varies with speed and load. And so optimizing mechanical and the control systems to optimize it. So you'll see more vehicles coming out with multi-speed transmissions, for example, rather than a fixed speed. And that's about keeping your motor in its sweet spot, its most efficient point. Driving style has a big difference. Those who drive EVs, if you're a bit lead-footed, you'll see that range diminish. If you're a bit more conservative, you can get a lot more out of it. But also like the BMS technology that we're involved in, about how you balance the cells, how you look after them, how you condition them, all has a huge effect on efficiency. So as time goes on, there are improvements. So if you look also even things like, you look at the development of the internal combustion engine, in particular diesels over the last 20 years, the efficiency gains have been amazing, but they have been tailing off recently, and you're getting to diminishing returns.
At one point there was some discussion about dealing with the range issue by having swap in and swap out batteries. Obviously, there's an issue about whether it's an old battery or a new battery, but putting that aside, where has that discussion gone to? And given that you're involved in the sort of modularization of these things, is that something which you're involved in?
It's not really a technology I favour. I mean, we're not blind to, everyone has to be open-minded about, in certain applications, it might be worthwhile. I think for privately owned passenger cars, personally, I think it's the wrong answer. One of the main protagonists, unfortunately, went bust eventually after huge investment. It was very focused around the mechanised swapping of a pack in a standard sort of architecture, and that's the only way you can do it, really. The technology was very clever, but ultimately, it didn't take in the market. I think if you're talking about, it really depends. I think for most passenger cars, it's the wrong answer. I think the physical challenge of removing something of that size from a vehicle structure is pretty challenging. You need the same shape and size in every vehicle. You need again the ownership challenge that you mentioned there, but the ownership of the battery could change. It could be leasing. You could change a business model such that you're subscribing to an energy model rather than the ownership of the battery. So those are solvable, but it's not something we favour. Really, our modular approach is such that we can have a standard design and offer it to lots of people, and maybe that there could be upgrades in future. But in most cases, you design it such that it can achieve the duty cycle you need during its working day, and then you can charge it either at night or at lunch stops or whatever. So, for example, the construction equipment we're looking at there, we've sized it for a day's operation, and that's readily achievable given the technology we've got now.
Thank you very much.
Thank
Stephen.
you.
I think we'll leave it there.
Cheers.